Our first speaker today is going to be Caitlin Pryor from the Oceania region. Caitlin is a graduate from the University of Queensland with a first-class honors in mechanical and aerospace engineering. Okay, that's great. She has previously worked in both the medical research and aerospace manufacturing, and will be soon starting work with Barn. Oh, anyhow, she's changing jobs, let me put it simply. So, Caitlin, it's all yours. Good luck. And
good morning, my name is Caitlin, and today I'll be talking to you about additive manufacturing, specifically my thesis topic, which was a comparison of desktop systems. This was conducted at the University in Queensland with assistance from QMI Solutions. Some of you are probably wondering what exactly is additive manufacturing, and I will go into that in a second. Then I'll follow that up by going over some of the case studies of where it's already been adopted by industry, before further going into details of what my thesis was and the outcomes of it. So what is additive manufacturing? It works so currently manufacturing, you tend to start with a large amount of raw material, and from there we cut it away, we melt it away, doing various actions, and there's a large amount of waste material. How this works is you start with your digital CAD file. It's put through various processes that take your model and slice it into successive cross-sections. And as you can see up there, a machine is then instructed to either, in this case, it's deposit some plastic in that particular locations, other methods of fusing powder together using either lasers or various other methods. Why this is quite interesting is not only are you able to use near net amount of material and therefore saving a lot of waste and money, it is also the fact that it reduces costs in product development. You no longer have to pay for additional tooling, you no longer have to wait for that tooling to be made. And also, the most important factor and most interesting to me is the freedom of design. You no longer are restricted by a large manual saying this is what your manufacturing process can and can't do, and you'll see that shortly. One machine can create a vast range of products, and this is starting to be seen in how the industry is changing their practices and looking through to adapt this technology into their use. The first study I'd like to present to you is one done by Airbus. This is a bracket found on the A320. And as you can see, it's gone through a great amount of change. The one in the back is made through traditional methods and is a very bulky item. What they did is they looked at what are the geometric constraints of this design, what forces are actually involved, and through successive amounts of finite element analysis, they were able to come down to this very different design that would not be able to be made in normal traditional manufacturing methods. Why this is significant is that they were able to save 75% of the raw material used. Not only does this create a 10 kilogram weight reduction per plane, it also means the lack of waste is quite significant to the extent that you have a 40% energy saving for this one part for its entire life. We can all appreciate with the airline industry as it is at the moment, saving money and particularly on fuel is a very important aspect. Another also interesting aspect that it does introduce is that you no longer have to stockpile all of these parts. The economies of scale with mass production at the one location are disrupted through this technology, and instead you can have a single machine at a single location to do the same job that a stockpile may have done in the past. The next study I'd like to introduce is a couple of medical examples. The medical industry has been very good at adapting this technology, particularly to customize for the individual patient. The example at the top is a skull prosthesis. Back in 2013, a man had 75% of his skull replaced using this technology. How this is created is they take x-rays and MRIs of the man's skull and then are able to create a perfectly fitting prosthesis just for him. Now that's great as it is, but it gets better. What they're able to do is through manipulating the 3D printing process, they were able to create a very porous structure for this prosthesis. Now that might be wondering why that's actually important. The reason for that is the bone is actually encouraged to grow into the prosthetic at that stage. And as a result, you no longer have to have additional surgeries later to tighten up prosthetics, to replace them, or various other things. That's quite common when it comes to knee and hip replacements. You quite often have to have quite a few years later, a follow-up surgery, they have to go in and change the replacement. With this, they're able to create a gradient between the bone growing into the prosthetic. You no longer have the harsh joining between the two of them, which makes it much more comfortable for the wearer in the fact that they don't end up with microfractures around the joining between the bone and the titanium, which is typically used. The next example is something you're probably all a little bit more familiar with. Many of us have broken an arm or wrist or had to have something put in plaster. These are uncomfortable things typically. You can't get them wet, they will smell, they're uncomfortable, they're itchy. No one enjoys them. With this, what's been able to do is it's customized to the patient through 3D scanning the arm, and on top of that, using the X-ray data to work out where the injury is. With this particular one, the person's injury was around the wrist, and as you can see, there is a greater amount of material in this area to reinforce that joint as it heals, and the rest of the arm is still immobilized as it would be normally. You can wash this brace, you can wear it quite comfortably, it's no longer hot and sweaty, and let's be honest, it looks a hell of a lot nicer. The next example I'd like to show you is not a commercial application, but it's a very niche design, and it's really fascinating. This is a strand piece designed by a Danish designer called Theo Jensen. And the really important thing about this is that was printed in one piece. There are a million, well, not exactly a million, but there are tons of little tiny moving parts in that. And they come in a range of sizes from about this small to this big. And to fiddle and try and assemble that by hand would be impossible. Although this isn't a very particularly commercial aspect of this application, imagine if this could be extended to commercial production lines. No longer do you have to worry about laborious, fine motor skill labor that's often straining on the person who's assembling it. You also save time and money. And the complexity of this is immense. This is what I was talking about before, and the fact that you can add complexity to these things and you don't have to pay a huge cost for it. The cost of this thing, I believe you can buy it online, and the one that's about this big is about $100, and a little one is about $30. You couldn't do that with any other technology. So let's have a look at desktop systems. In recent years, additive manufacturing has escaped from the confines of industry and has landed in the consumer and prosumer space. Desktop systems now can be bought from a couple of $100s up to about $5,000, and enabling students, hobbyists, small businesses, and education institutes to adopt this technology, play around with it, and see what they can do. Even though it's a rapidly growing market, little studies have actually been done on these devices in comparison to their industry counterparts, and this is where my thesis fits in. The two machines here were both owned by QMI Solutions, which this thesis was done in partnership with. They're a manufacturing consultancy, and they've observed some quite large differences in the final products of both of these printers. As you look at them, the hardware is very similar, and most of the setup of them was pretty much identical. So my job was to work out where was this difference coming from and what can we learn from it. Both of them use fused deposition modeling, which is the most common one for desktop printers, which is another reason why we looked at these two in particular. What it does is extrudes out molten plastic from a filament and lays it down layer by layer. It's, the video you saw before was an example of this. So as you can see on the screen, print quality can vary quite dramatically. But also it's important to look at what's actually required. Obviously, the cute little bunny rabbit on the screen is not quite having the same requirements as the Airbus A320 bracket you saw before. And that's something you really need to be taken into account as well. Desktop 3D printers typically aren't used for the high-end industrial heavy strength applications as the brackets are. And they're usually also limited to plastic materials. So this comes into what the analysis actually looked at. So obviously, print qualities are quite important. You need a good surface quality, not just to look good, but to also make sure that any future damage is prevented by having a decent surface to deal with. Dimensional accuracy is crucial. Not only do you want it to look how you intended, if it has an application that requires very low tolerances, you need it to be able to fit together, especially if it's something that's printed either fully assembled or is going to be assembled into something else later. And on top of that, strength. Although these designs typically on these printers aren't typically used for very high strength applications, there's quite a lot of research groups or various other institutions that are using them to concept test ideas that will eventually have a decent amount of stress on them. So it does need to be able to withstand concept tests. On top of that, we also wanted to have a quick look at the machines, work out whether there was something different between them else, whether it comes to time, material usage, cost, and see how that linked back into their performances. So looking through the literature, there's a myriad of different aspects that can affect the quality of a 3D print, particularly using fused deposition modeling. This will change with every different type of 3D printing technology you use, and there are many different ones. So I'll go through a few here. Firstly, layer thickness. This depends on the resolution at which you take your different slices, and obviously this has a great impact on especially surface quality, because if you have a sloping surface and you're stepping up, the finer you make that, the lower the roughness you'll get. On top of that, orientation is something that's very important with FDM printed objects. The reason for this is that because it is extruded and placed, deposited in a line, the strength lies within the direction of what's known as the raster. This is quite analogous to fiber reinforced composites. And as a result, you can use a lot of the similar strength calculations modified somewhat to understand what your final strength of your product will be. As I mentioned before, the raster is how it is placed and also the angle at which it's placed. Deposition speed is also quite important. You need to make sure you're not going too quickly or too slow, and that also comes into the thermal aspects of it as to how your part will cool as it's created, which can cause quite a few interesting problems later on. And the air gap. This is actually quite crucial because if the air gap is large enough that the rasters don't touch, you don't get strength transitioning between them. At the same time, often air gap is quite crucial to actually get the part to be made correctly due to the thermal cooling processes involved with the printing. So the testing. What we adopted was we used 3 test pieces, one of which can be seen on the screen. These were based on literature, existing test pieces, and ASTM standards that had to be adopted for 3D printing, as none of them existed for testing at this stage. The object you see on the screen is adapted from a door hinge from a Boeing aircraft, and it was used to represent something that typically may have been tested for size and fit on a printer such as this, which has happened at QMI in the past. It was also used to check dimensional accuracy, surface form, surface roughness. The other test pieces, which aren't shown on the screen, were used to test all of the strengths. So let's have a look at what actually happened. The instant you started printing along both of these printers, it was pretty clear to see that they took a very different print strategy. The cube, which is the one on the far side, has a very sparse setup. It's basically creating a thin-walled structure. On top of that, the support structures below overhangs and at various other stages are very sparse. As you can see, there's not that much material being used, and they've also got these little perforations on them. That's done so that when you reach an overhang, the support structure is easier to remove. Unfortunately, this proved to be insufficient to actually provide support to create a suitable model, which was unfortunate for that printer. The up, on the other hand, which is the closest one to me, that is a completely different strategy. They've gone for using quite a lot of support material, and they've used quite a high infill in comparison to the cube, which only used very sparse supports internally. This turned out to be one of the largest factors that actually affected the print quality, and I'll show you some examples now. So if we look at the supports, on the far side again is the cube, and you can see the perforations in the raft, and at this stage it doesn't look so bad. The perforations were very good at being able to remove the supports, but unfortunately the advantageous side of being able to remove them easily wasn't counted by the fact of good quality. The up on my side, again, what it did is when it had an overhang, it created a solid raft of plastic at that level. It was slightly more difficult to remove, but in doing this they were able to have a very smooth, very polished and very accurate surface at those stages, which is really quite important. So if we look at the surface quality, we chose to cut the model and look into it rather than just taking measurements of the surface, because during the printing stages we saw just how drastically different they were, and we wanted to compare what was going on inside as to what you were seeing. So as you can see with the one on the far side is the cube. Again, you've got the very sparse supports, and what you see is that as it was being built, you can see the waves on the edge, And that was able to be determined that there was insufficient support during the building process, that the next layer was not able to be accurate from the one below, and the errors kept on building as you went higher up, which is a problem unique to 3D printing, the fact that if you have a layer earlier on that does have a mistake, it's more likely to carry through. So that is a disadvantage with the technology that does need to be accepted. If you look at the one closest to me, the up, you can see it has a very high infill. It still has quite a significant air gap between the filling, but at the same time, the edges are very close to being perfectly flat. The surfaces were very smooth. You didn't have the same penetration of errors from the bottom layers to the top. And this just reinforced the fact that the inner supports were required more than what the cube had actually implemented. This here shows the overhang problem. On the one on the left, you can see that it's a very rough surface. You have a lot of parts hanging off, and in some areas, which you can see in the top corner of it, it actually has lost layers because they weren't supported and they completely fell away during the manufacturing process. This becomes quite significant if you're testing for dimensional accuracy or if there's a strength issue. You've not only lost a couple of millimeters, you've lost, it no longer looks nice, you've got a surface issue to deal with, and it's just not as strong. You did have some errors on the up printer. As much as the raft was able to make the surfaces very smooth and very easy to use and quite nice at the end of it, it did make it very hard to remove, especially from enclosed or slightly more difficult areas such as the inner cylinder there. So you do have parts where the raft was either left or during the post-processing to remove that, it did damage the part mildly. So there does need to be a balance between these two. There was also minor burns to the area. That was due most likely to some temperature control issues with the machine, but overall it did perform quite well. The strength actually to me is one of the most interesting factors, and it was at the time a little bit unexpected. I'll go through the flexural results first. For the up, it was quite strong. It had, for the plastic, it got 28 megapascals, which was somewhat expected for it. It fractured along the joins between the rasters in the same way you would expect a fiber composite to break. Everything was good there as it went along. Then we tested the cube, and something unexpected happened. It buckled, which when you step back and look at it, it does make sense. The printer created a thin-walled object, but the problem with that is that the test piece wasn't designed to be a thin-walled structure. So this raises an interesting point that really people do need to be aware when designing for 3D printers, is it's not just your design, it's also understanding how the print process works. The default settings may not necessarily be what you want, and you need to examine further. If it came to a situation where this product was being tested for a weight-bearing situation, this wouldn't display accurate results of what would actually happen in a real situation, because in this case, it wasn't accurately producing the part as required. This had similar impacts, similar results in the impact testing. The up was compared to an industry printer, and it was able to, as you can see on the graph, perform pretty much on par with it, which is quite impressive. Whereas the cube wasn't quite as good. And that was largely as a result of the fracture being able to transfer through the material faster than it was for the other printer. So in conclusion, additive manufacturing is a great new disruptive technology. You're able to save not only a large amount of material, you're able to optimize your designs in a way that wasn't possible in the past, and we're finding a lot of designs that are turning up that people hadn't even considered in the past, which is great. The freedom of design is amazing, and it also has other impacts that maybe at a first glance aren't considered, such as stockpile reduction, which not only saves people's time, but it saves a product sitting in a warehouse and degrading, and then someone having to check it and then realizing it's not going to work anymore. The major outcome from my thesis was not just the fact that the print process matters. It matters of understanding the exact nuances of each machine that you're using. It's not that one's better than the other. It's you have to make sure that you have the right settings for what you're using. And it shows that you need to understand the drawbacks and advantages of both. Thin-walled structures on a 3D printer are an amazing application, and there's some very interesting studies where this has been used very well, but you need to be aware and you need to design appropriately for it. Thank you very much.
Thank you very much, Kathleen. I think it was a very interesting presentation. I think before, my idea is that apart from the judges here, we will allow the members in the audience to also ask some questions if there is time available. My simple question is only on the materials. See the two examples you showed of the aircraft parts. Obviously, I presume they were some kind of aluminum alloy. Has this process been used on, let's say, high alloy steels also?
I'm not quite sure on which alloys it hasn't or hasn't, because the research with the materials on 3D printing is quite rapid. I know that titanium alloys have been researched quite a lot, and they're being quite successful with printing at the moment. I'm not sure with the steels. I believe that some of them can. Again, I don't know all of the literature behind it, but there is definitely moving towards that. The drawbacks with it is because the methods used to create metal products, it's a laser sintering process. So you have a bed of very fine powder of the metal. It's heated to near melting point, and then a laser is used to melt a particular point. It's really quite a fascinating technique to do, but as a result of how it's made, it has very different fracture patterns to traditionally manufactured metals, and that's where they're mostly looking at the moment, is to get a high enough strength to be used in the applications where it currently is, and also to fail in a safe way. Typically with steels and how they use its design so that you see the flaw or the crack before it will break. What they're trying to do with 3D printing is get it to a stage where you can see the flaw before it breaks. At the moment, one of the problems is that it won't spontaneously fail, but it won't give you much time to notice that it's going to fail, which is one of the current drawbacks.
It's a very interesting presentation. Could you tell us a little bit more about your sponsor company and what they're going to use your research and work for? What's their use of 3D printing?
QMI Solutions is a small consultancy in Brisbane. It's the printers that they use on their site at the moment is largely for when they're working with clients, and so they'll mock up things for them, and that's the main use of those two printers. They were the main company that brought 3D printing into Australia, so one of their roles is to promote 3D printing and where its opportunities can be used throughout the industry. So my research is more so that they can, when they go to customers, they can explain right through from the prototyping stage to the end and explain this is how the printer needs to be used, this is what you need to be aware of, and then at the same time they can also show them, it's like, here's the data for it, make sure that when you're testing for this product, you make sure that you've got the correct settings to at least get a scalable representation of it. So that's where my current research is being used. Yes?
But just give one comment on that is basically Rolls-Royce already uses 3D printing technologies for using metal to make
Yes.
it vibrate. And according to what you present here, I just would like to ask, do you think there's any geometrical concern by using your technology to make products? Because you're still talking about you go through the X and Y axis to make your products out, okay, by using the polymer. You melt the polymers, it's very cool. But do you have any geometrical concern on that? Or any shape the product can make?
So I'm just confirming, you're asking whether I'm worried about products being made with 3D printing, or?
Yes. The technique you just mentioned about, do you have any geometrical concern? Because
I don't.
Because for it to be able to, for the example, you said Rolls-Royce with their engines, and that's one of the really interesting applications they're using it for. For it to be able to put on the aircraft with that, it has to go through the same testing that anything else has. And I don't know, I haven't read all of, obviously they don't release much from Rolls-Royce, it's kind of annoying, I would love to read that kind of stuff. But it has to go through the same testing, and with my familiarity of how it's made, I'm quite confident that it's at a standard that can be used. There's a lot of, with the side of the metals, which is what they're predominantly using, there's a lot of post-processing that goes on to make sure that once you've got the product that you want, that it's then at the correct strength and correct mechanical properties, that it's going to be used and it's going to be just as strong as the one you had before, and if not better.
Yes. I've actually got two questions. One is, I've seen a lot of news research into 3D printed houses in disaster zones. Do you think this has any possibilities, or is it just a nice idea?
Yes, for both of them. It is a very nice idea, and it's a concept that needs to be explored. 3D printing for housing it's the ones that I've seen are basically they get a concrete truck up and they basically print it in a slightly modified version of that. You can knock up houses pretty quickly with it. The problem with that is that you have to get a lot of infrastructure in there to be able to print the house. So the research for that is really fascinating, but it needs to get a couple more iterations through before it's actually useful in a disaster zone, unless that disaster zone happens to be next to the university that's currently researching it.
Is you mentioned with the other complex structures that one this size was $100 and one this size was $30. Is there any more engineering work that needs to be done for that, or is that cost implication purely just?
It's a combination of the materials that are used, and there's the company that it's sold through is called Shapeways, and it's an online marketplace for 3D printed products. You can create your own store if you've got designs, or you can just buy someone else's, and if you want to get your own stuff printed, that's fine. So the pricing is a little bit hard to tell because it's partially the designer's put a premium and it's hard to work out where he set that. It's a combination of how much space it takes up in the printer, how much material it uses, and there is a premium for how much space and the density at which it uses for that. Obviously, if you're not using that much material but you're using a large amount of space, the company can't make as much money off it, so they're going to make you charge a little bit more for it. But it's quite useful in the fact that, yes, you can get a design that's really complex and make a little one. I've got one that's to my desk and it's great fun to play with, but you can also get one that can chase a cat.
Okay, I think time's up. We have to be. Thank you very much, Caitlin.